Hello, everybody. I'm Scott Petersen from Adobe Systems. I work on the Air engineering team, Air being the sort of desktop flavor of the Flash runtime, allowing you to do things like build applications with installers that can do things like access the file system, databases, all the sorts of things you wouldn't want to be doing in the browser. And I've been working on a kind of neat use of LLVM that's a little bit different from some of the other things we've seen. It doesn't involve generating any sort of machine code, and it doesn't involve C or C++. It really only involves ActionScript 3, which is the language that is used to develop against Adobe's runtime, whether it's the Air runtime or the Flash player. And I'm going to give you a sort of really quick overview of ActionScript, just to give you a flavor of what that language is like. And it's very similar to JavaScript. It's actually ECMAScript based. It's essentially JavaScript with classes and types. So I've got a couple of little bullets there that show you, where in JavaScript you just have var x, which is implicitly a variant type. Could be a string, could be an integer, sort of anything. There are actually type annotations in ActionScript, so you can specifically type a variable as an integer, or if you do want it to be a variant, you can tell the compiler, I haven't forgotten to type annotate this. I really do want it to be a variant. And what the Flash player, the Air runtime, actually executes is a bytecode. So unlike the browser, it does not actually suck down source code, lex, parse, and then actually execute from there. It is compiled ahead of time to an ActionScript bytecode that is fairly reminiscent, actually, of Java bytecode. So it's verified, it's stack-oriented, it's object-oriented, push A, push B, add, sort of that kind of thing. And being designed for the Flash player, the execution environment it's pretty neat. It's got a very small footprint because, of course, we like to keep the download footprint of the Flash player and the Air runtime down. And actually, the JIT compiler, the interpreter, garbage collector, basic support libraries, all of that stuff is only about 600K compressed and only 1.5 megs uncompressed. And this portion of the Flash runtime is actually open sourced. It's the Tamarin project that's hosted by Mozilla. So you can actually go and check it out, build it, play around with it. It's actually quite a neat little VM. And the compiler is a fairly straightforward compiler written in Java. So it's recursive descent, doesn't do a whole lot of optimizing, really just kind of generates a parse tree, spits out a bunch of ActionScript bytecode. And for that reason, ActionScript performance, well, for various reasons, but that is one reason that ActionScript performance is, not super close to native performance. So if you look at the performance of kind of regular old ActionScript compiled to this bytecode and run through the JIT, it's roughly, for sort of numeric compute-heavy stuff, about 1.2% as fast as if you had compiled an equivalent program natively in C and executed it straight on the CPU. But part of that is limitations of the VM, but part of that is also inefficiencies in the bytecode. And one of the pieces of data there is that another LLVM project that I worked on is the Alchemy project. And what that did was essentially take C and C++, run it through the Alchemy toolchain, and spit out this ActionScript bytecode. So you could actually take C and C++ programs, compile them using LLVM, and run them on the Flash player. And so the performance there, running on exactly the same VM, just with different bytecode, is roughly 30% of native optimized C, which is obviously substantially better than 1.2%, and is actually about half as fast as Java running on Sun's JRE6. So that's actually not too bad. And again, it's running on the same VM that ActionScript itself runs on. So C code running on this same JIT is about 20 times faster than ActionScript code running on that JIT. So why is that? Why is the C code so fast, and why is the ActionScript code so slow? And there are various reasons. The code generated by Alchemy from C code avoids some of the known limitations in the JIT or known inefficiencies in the execution model. So again, ActionScript has this variant type, and boxing and unboxing of those types it's very expensive. It's a very expensive operation and can even involve allocations in some cases. So the way Alchemy generates its bytecode is it just totally avoids variant types. It strongly types everything everywhere all the time. ActionScript code, it's an object-oriented language, again, very similar to JavaScript. So it's very common to do lots of object creation, lots of arrays, lots of news. And that taxes the garbage collector quite a bit. And the garbage collector is often in any JIT, one of the, or any managed memory environment, often one of the components that takes a lot of CPU time. And the way Alchemy avoids that is by using kind of a virtual RAM that it just reads and writes bytes and integers and so forth from. And so that, again, avoids taxing the garbage collector as much as sort of regular ActionScript code. And there are a couple of other limitations of the Tamarin JIT. It's not as good at parameter passing as native C code would be. And of course, it allows you to do totally dynamic stuff. Like, JavaScript lets you do bracket, quote, whatever. And that has to be a runtime lookup. So Alchemy doesn't do any of that. But one of the other reasons that Alchemy generated code is so fast is that it takes advantage of LLVM's optimizations. And again, the ActionScript compiler that we have today does very little optimizing. It's effectively a non-optimizing compiler. So could we use LLVM to do some of those optimizations rather than having to reproduce them ourselves in modifying the Java ActionScript compiler? While some of LLVM's optimizations don't apply, things around pointers and memory and so forth, obviously doesn't directly apply to a language like ActionScript. But a lot of things do apply. In fact, probably most of the interesting optimizations do apply to kind of almost really any sort of code. But of course, LLVM doesn't understand ActionScript, and it doesn't understand the bytecode format. So to build an ActionScript optimizer on top of LLVM, we sort of did the reverse of what we did for Alchemy. So where Alchemy goes from C to LLVM bytecode and then to ABC, we go from ABC to LLVM's bytecode, run some optimizations, and then bring that back into ABC that we can then execute on the same JIT that's on 99.9% of people's machines in the Flash player. And so it's actually relatively straightforward. We take our ABC, we turn it into a fairly ActionScript-centric SSA representation, and actually, thankfully, I did not need to even do that part. There's an open source tool that is part of the Tamarin project called Global Optimizer that was written by Edwin Smith of Adobe that already knows how to take ABC, build an SSA representation out of it, and actually even do some amount of analysis and optimization. So we'll do SCCP, we'll do some basic DCE, and we'll do some sort of basic type analysis on it. And so we can take that SSA representation and convert it to and from LLVM in a relatively sort of straightforward way, with the caveat that we are not generating LLVM IR that will actually run anywhere. And we can then run the optimizer against that and bring it back into the ABC SSA representation, and again, use the global optimizer code base to generate something that can be executed in the Flash player. And so to generate IR, LLVM-flavored IR from our ActionScript-flavored IR, we essentially generate some types, the most obvious one being some type for ActionScript's variant that can hold strings, objects, whatever. Generate an LLVM function for every ActionScript function. Pretty obvious, pretty straightforward. And then what we do is, for each ABC opcode, we basically just invent a call for it. So For example, if you're creating a new object, well, we just invent a function that's called new object, and we just call it. And we claim that it returns something called an AVM2 value, and maybe we claim it takes certain parameters, but really that function doesn't exist, nor is it ever going to exist. It's just sort of a placeholder for LLVM to be able to process this IR generated from the ActionScript. And we can actually give LLVM a little bit of ammunition to be able to optimize a little bit better with these sort of black boxes by setting some of the memory side effect characteristics like read none, read only, etc. on these functions. And of course, obviously control flow you would convert directly to LLVM IR. Now where it gets a little bit more interesting is that for certain types of operations that have sort of obvious analogs in LLVM's IR, like any sort of arithmetic, we have, again, these sort of phony, not really existent functions that know how to convert our variant type into things like integers or doubles or something else interesting to the LLVM optimizer. So for example, for the ABC opcode add I, which is an integer add, we insert two calls to a sort of fake unbox this variant into a 32-bit integer, have an actual LLVM IR add, and then we rebox that. And we can, when doing these conversions, use some of the type information gathered by the global optimizer to know that something is an integer or something is a double, etc. And the other interesting thing is that when you have a call in ActionScript, in some cases when it's not a dynamic call, when it's statically known to call a specific method, we can turn that into an LLVM call, allowing the optimizer to do things like inlining and so forth. And of course, with all of this sort of perfunctory boxing and unboxing, we need to be able to collapse some of that. So for example, if you had two adds or something, you would end up with this huge amount of code that's boxing, unboxing, adding, blah, blah, blah. But really, you just want to sort of have the two adds chained together without all the boxing and unboxing in the middle. So we have a special pass to eliminate that. So here's a very simple ActionScript function. So it's called copy matrix, and it's from one of the, I believe it's from one of the SciMark performance tests, and it's really just copying from one array to another, and you can see here the type annotations. And it just takes three parameters, the two arrays that it's copying to and from, and there's an implicit this parameter for any method in ActionScript, like JavaScript. So pretty straightforward. It's just got a loop. It's just copying stuff around. So what does that look like as ABC? Now you don't need to sort of read this whole thing, but just to give you a flavor of, again, the stack machine, you can see that it's grabbing its parameters, pushing those on the stack, doing gets and sets, and accessing various properties by name, all sorts of crazy dynamic stuff. And this is effectively what we take and convert into LLVM's IR. And so this is, again, the same function as LLVM IR. And again, you can see, and I have here at the top just some of the fake functions that it uses, get property, set property, annotated with memory access characteristics. And it's roughly a transcription of the actual opcodes in the ABC, just converted into these functions that are represented in LLVM's IR. So how did we do? We wanted to get, 20 times faster, right? Alchemy-generated code is 20 times faster than the regular ActionScript code. So how much of that was actually due to LLVM's optimizations, and how much of that was due to avoiding some of the ActionScript VM's inefficiencies? So we didn't quite get 20x, unfortunately. This is the untyped SunSpider benchmarks, and you can see there are some cases where there's some meaningful improvements. Almost 40% for 3 bits in byte. You can see, 20-something odd % for NCV bits, but not 20x, not really even 2x. And you'll see the same thing for, again, the SunSpider benchmarks, but now typed with the ActionScript type annotations. You know, again, there are a couple of cases where we see some real wins in partial sums. We're getting 40% faster, but also there's some cases where we're substantially slower, which is sort of strange. And so where's my 20x speed increase, or at least a 2x? This is what my boss asked me. And it turns out, you know, once you sort of profile the entire system, that even well-optimized ABC code, execution time is still very heavily weighted towards a lot of overhead types of behaviors. Allocations, which in some of the cases is up to 50%. So this is actual allocations and garbage collection behavior. Almost never is it much less than about 25% of the entire CPU time being spent with allocations or collections. Accessing ActionScript arrays, which are typeless and therefore always store variants and always are going to have to be doing boxing and unboxing. Up to 75% of execution time in one of the worst cases, and over 50% in a number of cases. Dynamic property lookups, again, you know, depending on the test, it can be a huge amount of your execution time. And these are all things that optimizing the actual bytecode is not going to get around. I mean, if you're doing a fast Fourier, you're going to be touching the array the same number of times, no matter how you rotate your loops or whatever else. And so again, value boxing is another huge piece of overhead. And one of the more interesting results, and this accounts for some of the actual drops in performance, is that the actual VM does very simple type analysis to figure out when something can be represented purely as a 32-bit integer or purely as a double, and therefore doesn't have to be an expensive variant that may have to live on the heap. And you can actually change control flow such that the VM can no longer determine that this value, this local whatever, is always an integer, and actually will lower performance by then representing that as a variant that has to be allocated and tracked and pointer dereferenced and all of that. And of course, again, parameter passing in the VM remains expensive, although in some of the cases where there were some big wins, that was due to LLVM being able to inline some of the ActionScript functions into other functions, getting rid of some of that overhead. But still, I think it's still kind of a promising result that you can actually get LLVM to optimize something that is not C, is not targeting an actual CPU, but could be, you know, bytecodes from the parent VM, or it could be, you know, Python's actual bytecodes, anything like that. And factoring in some of those huge amounts of overheads, you know, those sort of 20%, 40% performance increases overall are actually representative of more like, you know, 50% or 2x speedups in computation proper. So some of those optimizations really did affect positively the compute CPU consumption of some of that code. It was just dwarfed by some of the overhead. So I think some of the obvious future directions that this work suggests is, you know, a lot of that overhead is something that really needs to be addressed. So the VM type deduction, allowing it to use native integers or floats or whatever instead of variant types in more cases, is something that would have, I think, made the results of the optimization a lot more pronounced. Continue refinement of the garbage collector, which of course is something anyone who works on any sort of managed memory environment is continuously doing. But I think LLVM could be used in a little bit less straightforward ways to address some of these problems too. You know, we could enable accurate garbage collection to reduce the garbage collector load in a lot of these cases. Maybe even do escape analysis to reduce allocations of variants or arrays or, you know, objects or kind of anything else. And it's probably possible to use some of LLVM's analysis capabilities, even if it doesn't know how to do these types of transformations. We could still use some of the infrastructure built into LLVM to help us write AS3 specific optimization, so AS3 specific type strengthening, or maybe identifying arrays that only ever have integers put into them and therefore don't need to be built to hold variance. You know, arrays with bounded sizes, people using prototype style object-oriented coding instead of using real classes. Or things like explicit object deletion opportunities, again, sort of reducing the load on the garbage collector. And one of the other kind of interesting things about this is that if you take those kind of fake function calls that are representing the ActionScript bytecode opcodes and, you know, sort of write implementations for those, well, you have kind of most of an ahead-of-time compiler for ActionScript. And so you could, in a relatively straightforward manner, kind of, you know, instead of calling some fakey thing, call some real thing in the core, and be able to compile natively your ActionScript code. And this is sort of just taking the project in the direction that a lot of other people are doing with, you know, Python and Ruby and so forth. And, you know, like those projects note, you can do some pretty cool stuff in a scenario like that. You can build the VM as bitcode, build your application code as bitcode, link them together, allow pretty straightforward inlining of pieces of the actual core's implementation in pieces of the application. And that could be used to do, you know, all sorts of interesting things. You could build native versions of entire Flash applications, or maybe just build native versions of some very common Flash libraries, like, you know, the Flex library, which a whole lot of applications use, and, you know, is continuously being JITted and rejitted and rejitted when you really could just have a native implementation of it. Install time, native code gen for Air apps, sort of along the lines of what you can do with CLR. And potentially, this obviates the need for any sort of JIT at all. So it's a potential path for Flash or Air applications to run on platforms that either can't or don't want to support just-in-time compilation. And I think that's the end of my presentation. Does anybody have any questions?